Hi, welcome to the next video for the first topic of Year 11 Chemistry. This one's going to combine a couple of things together from subtopic 1.2 and 1.4, and this is going to be all about electronic configurations. Now, if you're thinking about electronic configurations, the first thing you need to understand is how many electrons each electron shell can hold. Now, there's a special rule for this that we call the 2n2 rule. So what I'm actually going to do is see if I can get my little pen up here, and I'll just draw it in if possible. So we're going to go with the, whoops, I'm going to draw over there. So the 2n2 rule. Now, sorry, it's really difficult drawing with my touchpad at the moment. I have my mouse with me, but hopefully you can see that we've got a 2 and then n is the shell number and then squared. So what we're doing for the 2n2 rule, okay, is that we're actually going to be looking at using the shell number here, so electron shell of 1, okay, so 1 squared is 1, timesing up by 2 gives us the maximum number of electrons that we can hold in that shell. So as you go down here to the 5th shell, 5 squared is 25, 2 times 25 tells us that the 5th shell can actually hold a maximum of 50 electrons. Now that's important to remember when you're first working out what we call the simple electron configuration. Okay, so a couple of things you're going to use from the periodic table as well. All right, we look at the period number. Okay, so if it's in period 1, 2, or 3, or 4, that tells us how many electron shells we have. We look at the group number. That tells us the number of electrons in the valence shell, or the very, very last shell. Okay, so keep those two things in mind: period number, number of shells; group number, number of electrons in the last shell, and then we use this formula here, 2n2, to work out how many electrons we can get in each shell. So the simple way to do a basic electron configuration is, again, use the period number to tell you how many electron shells there are, then fill each shell to its maximum number using the table on the last slide. Okay, so I'll show you firstly. Selenium is atomic number 34, it's in period 4. So we're going to have 4 shells, and what we're going to do is fill up each of these shells. So back on this slide, we saw that the first shell can hold 2. Okay, so the first shell has 2. The second shell can hold 8. All right, here can hold 8. The third shell can hold 18. So here we've got 2, 8, 18 as we go through. So if you add those up, that's going to give you 18 plus 8 is 26 plus 2 gives you 28. So we've got 28 electrons so far here in these first 3 shells. We know we need to get to 34 because the atomic number tells us the number of protons, but also the number of electrons in a neutrally charged atom. Now the group number tells us how many electrons are in the last shell. It's in group 6. Yeah? So group 6 tells us it's going to be 6 here, but we could have worked that anyway because 2 plus 8 plus 18 gave us 28. The difference between 34 and 28 is 6, so that's how many are in the last shell. So the simple electron configuration is 2, 8, 18, 6 for selenium. So you could do this with any of the elements in the periodic table, just using the group number and the period number, and working out a simple electron configuration. However, we don't use those really when we're talking about electron configuration in chemistry, because those electrons in those shells actually have different orbitals, all right? And so, and there's different energy for those electrons. So even though there's 18 electrons in that third shell, they don't all have the same amount of energy. So there was a scientist called Erwin Schrödinger. He determined that within each electron shell, there are actually smaller subshells where electrons exist. So he determined that there was an s orbital, a p orbital, a d orbital, and an f orbital. That's why sometimes when you see structures of the atom or diagrams of the atom, you'll see that nucleus in the middle, and you'll have all those electrons that are flying around it in different directions. That's because he worked out there was different orbitals and energy levels that they exist. Okay, so those orbitals relate to the periodic table really well. So anything in group 1 or 2, their highest electrons exist in what we call the s orbital, so they're called the s block. The transition metals, they have electrons in the d block, and the non-metals over here, they have their highest electrons in the p block. Okay, there's the lanthanides and actinides down here, which are the f block. We don't look at those in year 11 at all chemistry, so I say F for forget me block. All right, just don't worry about it. But the different parts of the periodic table actually relate to electron subshells. So S block have either 1 or 2 valence electrons in their outer shell. okay, and their highest electrons are in the s orbital, as we said. The p block, all right, groups 3 to 8, so it's all the non-metals over here mostly, with a couple of metals through here as well. The highest energy valence electrons are in the p subshell orbital, and they can hold a maximum of 6 electrons. Okay, so the s orbital can hold a maximum of 2 electrons. Here, the p orbital can hold a maximum of 6. So inside your second shell, the second shell can hold a maximum of 8 electrons. There's actually an s orbital which holds 2 and a p orbital which holds 8. And altogether they make 8 electrons in that second shell. The d orbital or the d block is the transition metals that can hold a maximum of 10 electrons. So now when you look at your third electron shell, which can hold a maximum of 18, that has an s that holds 2, a p that holds 6, and a d that holds 10. 2 plus 6 plus 10 gives us 18 electrons in total in that one third shell. So this is the little diagram that I use for my students. Hopefully you'll be able to use this reasonably easily as well. And this is what I say that you do to write what we call subshell electron configurations. You just have to follow the arrows. So we start off, there's a pattern to how this goes. So it's 1s, then you go 2s, and you add 2p. Then you go 3s, 3p, then you add 3d. Then you go 4s, 4p, 4d, but you add 4f. So you're just adding an s, p, d, f each time. Then what you do is you follow the arrows. So we're going to do 1s orbital first, then 2s, 2p, 3s as we go. Sorry, I don't know what happened there. Okay. And so the reason I've only gone up here to the 5s and we don't have the arrows going over this way is because the 5s is the highest electron shell we need to go to, because 5s2 will give us strontium, and that's an atomic number of 38. That's the highest you have to know in terms of electron configurations. All right, there we go. Sorry, I just zoomed in for some reason there. So to write them, firstly find the atomic number, okay? Then start filling up the subshells in order using these arrows, okay? So follow your way through. So you might want to screenshot this or clip it or something like that, or write it down. Keep that as a little side note for you while you're doing your electron configurations. So find your atomic number, fill up the subshells in order. So the S shell can hold 2, P can hold 6, and D can hold 10. So an example is calcium, atomic number of 20. Okay, so we're going to start with, over here, we're going to start with the 1s. The 1s can hold 2, so we're going to go 1s2, then 2s2, 2p6, because this can hold 6, 3s2, 3p6, okay, and then 4s2. And you keep going until you get to the maximum number here. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So that's our what we call subshell electron configuration for calcium. So if you have a look at the number in front, in the first shell there's 2 electrons, which is what we had before. In the second shell there's 2 plus 6, which gives us 8. In the third shell there's 2 plus 6, which gives us 8. And in the fourth shell there's 2 electrons, which gives us 2. So if you did this the simple way, firstly, of looking at calcium is in group 2, so there's 2 electrons in the outer shell, and it's in period 4, so there are 4 electron shells. So 2A82 is exactly what we've done here. We've just broken it up into those subshells. I'm not going to go into any more detail than that, but there is this video here if you want to have a look at electron configurations part 1 that goes through this in a lot more detail and gives you some more examples. There are 2 important exceptions for this, okay? So that's chromium and copper. So if you were going through and doing this normally, what you would end up with for chromium is 4s2, 3d4. And for copper, you'd have 4s2, 3d9. I'm not going to go into reasons here of to why these are 4s1 and instead of 4s2. Basically, it's to do with pairing up electrons in the different subshells. That's university chemistry. You can ask your lecturers about when you get to uni if you want. But all you need to know is that the chromium and copper in the transition metals, they have 4s1, not 4s2. So just try and remember that. And that's something you're expected to know in year 12. So if you learn it now, you're much better off. If we're going to write the electron structure for an ion, though, it's very, very similar. There's just one extra step. So write the normal subshell notation for the atom. So like we did for calcium with 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Okay. Then work out the charge. Now calcium, because it's in group 2, would have a 2+ charge. Okay. So that'd be the charge on it. So if it's positive there, we take the electrons away from the highest subshell first. So for that calcium, we take them away from the 4s orbital. If it's negative, you add electrons into the highest subshell. And what you're trying to do is to get the outer shell being full. So there's another video here on this, which goes through some details and more examples, but I'll give you one example now. So here's chlorine, atomic number of 17. So it'd normally be 1s2, 2s2, 2p6, 3s2, 3p5 if we follow the arrows through. Now, because it's a non-metal, it wants to gain electrons. Because it's in group 7, it has 7 electrons in the outer shell, which means it wants to gain 1. So we need to put 1 in. So because we're putting electrons in, we find the highest subshell, which is the 3p here. We put 1 electron into here and we get 3p6. Now what that does is that gives our whole third shell, 2 plus 6 equals 8 electrons in total. So our third shell is now actually full with 8 electrons. So this is the simple arrangement, 2a8, but the chlorine ion is 1s2, 2s2, 2p6, 3s2, 3p6. Okay, the outer shell, the third one, is full. That's really important. Okay, give you another example here of zinc. Okay, zinc has atomic number of 30, so its normal electron configuration is this, 1s2, 2s2, all the way up to 3d10. So this is full, okay, here at this third shell, and then the fourth shell here with 4s2. The charge on a zinc is 2+. It's a transition metal. If you remember from the periodic table one, I said to remember that most transition metals have a 2+ charge. But the key you got to remember on that previous slide is that you either add them in or take them away from the highest energy subshell. Not the last one, but the highest energy one. So the highest is actually the 4s electron here. All right, so we're going to take those 2 away. So that's actually the outer shell. We take those 4s electrons away, and now we end up with 10 plus 6 plus 2 is 18 electrons in that third shell. The third shell can hold a maximum of 18, so that's full. So the key with transition metals is to remember that they're going to lose their 4s electrons first before the 3d ones. Okay, there's some more examples of that in that video I showed you before as well. The final thing we're going to be looking at is how from these subshell electron configurations you can get information of where an element is in the periodic table. So if all we had was this electron configuration here, we would be able to tell that because there's a 5 here, the highest shell is 5, so that tells us the period number. That tells us how many shells there are. This S here, in that shell, the highest one we have, the highest subshell is the S, so that tells us it's in the S block. Okay, and how many electrons do we have in that subshell? We have 2, so that tells us that is in group 2. So this one here, 5s2, tells us that it is in period 5, group 2, the S block, and it is strontium. So you can actually use this any way you want. If we just had, for example, this first bit here, so 1s2, 2s2, 2p6, 3s2, 3p6, if we just had this, the highest shell is the third shell, so that would mean it was in group, period 3. We have 2 plus 6 gives us 8 electrons in that shell, so that would make it in group 8, okay, and in the P block, so this would actually be one of the noble gases. All right, so hopefully this has been reasonably straightforward for you and you've been able to get an understanding of how we do electron configurations in chemistry. You might want to watch it a couple of times. You might want to go into a bit more depth with the other videos I've got as well. But as always, if you've got any questions, just ask. Thanks, guys.